Okay, let's do this question. This question is give me a hard time. So you're given a network of nodes represented by this adjacency matrix. So 1 if the nodes are connected, and a 0 if the nodes are not connected. And the nodes are corresponding to the index within this matrix. And you're also given this vector of initial nodes, which represent nodes infected by some malware. And if two nodes are directly connected to each other, then they're both, and one of them are in the initial vector, then both nodes are infected. So we want to find out if we were to just remove one node from initial, which node should we remove so as to minimize the total number of infected nodes? So there is a very tricky case here. So for example, if you take say node 1 is connected to 2, which is connected to 3, and we also have a node 0 here that's not really connected to anything. And we have that node 1 is infected, node 3 is infected, and node 0 is infected. So we have 0, 1, 3 is our initial nodes. So which one should we remove from initial such that so as to minimize the number of total infected nodes? So if we consider all nodes are in the network, all infected nodes, the number of infected, the resulting graph will have all nodes infected because 2 is connected to 3 and 2 is connected to 1. So if we were to move, say, 1, for example, the number of infected nodes we remove is 1, because 2 will still be infected because it's still connected to 3. Same case if we just remove 3. In same case, actually, if we just remove 0, all of them are still infected. So what do we do here? Which one to remove, since all of them kind of remove the same number of infected nodes in the resulting network? Then we should return the node with the smallest index, so we should return 0 in this case. Let's consider another case. We have 1 to 2 to 3 and to 4, and we have that, let's say 2 is infected and 3 is infected. And we have 3 is also connected to 5. So the obvious answer is 3, right? Because if we remove 3, then we get 2 less nodes infected in the final resulting graph. And when we remove a node, it also removes the edges as well that are connected to that node. So that means 4 and 5 will no longer be infected in the resulting graph. So we kind of see that the number, if we can count the number of nodes that belong to an infected node, that uniquely belong to an infected node, is the highest for, then we select that node to remove. So for example, 3 is connected to 4 and 5. There are 2 nodes that uniquely belong to 3, and 1 is uniquely belongs to 2. Now let's see what happens if 2 and 3 are both connected to a node 6 here. Since 6 belongs to both 2 and 3, they both can be touched by 2 and 3. Then 6 doesn't uniquely belong to 2 and 3, so we don't count 6. And that kind of makes sense, because if you remove 2, 6 will still be infected. So If we remove 3, 6 will still be infected because 2 is still there. And the other thing to note is if 3 is... When we try to find what nodes uniquely belong to 3, we can't find 1 because to find 1, we would have to go through this infected node. So we try to avoid going through other infected nodes to find other nodes. Yeah, and that's basically it. So what's the time complexity of this solution? Well, we can do a DFS from each infected node, and we can have a counter for each node and just increment a count. And so then eventually this one here will have a count of 2, 4 and 5 will have a count of 1, and 1 will have a count of 1, and then we have to do a DFS for all infected nodes again, and just count the number of nodes that we see that have a count of 1, and if we see a count of 2, then we just stop. If you see a count of greater than 1, then stop there. It's like a return condition. So DFS, to go through this graph is like a 300 by 300 matrix. So the n goes up to 300, so that's like 300 squared that's 300 squared edges. And DFS is the complexity of DFS is v plus e, where v is the number of vertices and e is the number of edges. And we have to do this DFS for all the initial nodes, and initial nodes can go up to n as well. Or let's just say it can go up to n, so that means our final time complexity will be something looking like this, n cubed. N cubed, well, 300 cubed is like 27 million, and assuming that the time the time limit is 1 second or something like that, we should be able to solve this problem in time. I mean, fast enough. Why? Because if we take a rule of thumb that 10 to the power of 8 is the number of operations that we can do in 1 second, in 1 second, then then 2 to the power of 27 million is 10, let's say times 10 to the power of 6. That's definitely less than 10 to the power of 8, so we can do this in 1 second. Alright, so let's start coding this up. To check if a node is infected or not, it's best to have this initial node in some kind of unordered set, so we can figure out if a node is infected in constant time. Say infected, and go, alright, so for int I in initial infected.insert I. We also need to keep track of the count of the vertices, so vector int count, and we need to go through we need to do a DFS on each of the infected nodes. And make sure we need a scene array, so we don't, our time complexity doesn't go overboard. Maybe a boolean. and we could say maybe keep track of n as n is equal to the graph.size. So graph.size is the number of nodes. Then we can say count is equal to a vector int size n and starts at 0. And we also have the scene to be equal to the vector of booleans okay. So we need a DFS that will increment the count for a particular node, for a particular infected node, starting at say v, and we also need access to the graph. So if we've seen this before, should be a vector of boolean. So if we've seen v before, then return otherwise set scene to equal to 1 or true. What else? Count of v should be incremented, and then we have to go through each of the connected nodes. So for int I is equal to 0, I less than n plus plus I, going through each of the infected nodes. So the graph of v at I, if that is 1, right, then do a DFS on this node, which is I, which might say u. So u is better. Okay, cool. But so this has to be done for each of the initial nodes. So for int u in initial. Oh, and also I don't, if the node is infected, so if u is infected, then skip it. So I could skip it up here. If yeah, I can skip up here, I can skip it down here, it doesn't really matter. So if infinite.find, so trying to find u is equal to does not equal to end, so infinite.end, that means, yeah, actually I want it down here, because if I put it down up here, then that means I want the first one that I pass in won't be would exit immediately. Then I want to continue. Cool. And then here I want to go through for int u initial. So for each of the initial nodes, I want to do a DFS on that, pass in the graph and u. Yeah, and that should initialize the counts for me. And now I just need to return a count, and that takes in vector graph int v. So let's do we're doing a DFS, so we probably need to every stage clear out the DFS. So fill n fill the scene vector, so begin scene.end with false. So I haven't seen it yet, and do this. You need to go through all the nodes, so all the infected nodes again, and keep track of the best answer. So the answer is answer, and let's say the count is equal to -1 initially, and we do DFS count, max count here. So you can say int count is equal to DFS count on graph with v, which is actually should be u. Okay, so if the count is less than, it's greater than, if the count is greater than max count, or the count is equal to the max count, and u is less than the answer, then I want to update the answer to be equal to u and max count, and at the end return the answer. So this part makes sure that we're returning the smallest index. And here I need to do it if scene v return. So here I'm doing DFS, so I need to make sure I do this line here, because I'm doing another DFS, I have to do this again. And let's go through here. If I've seen it, return. Otherwise I've seen it, so set it to scene. And also so go through all of the nodes again, all the connections. If it's an infected node, continue again. And also if the count of u is greater than 1, continue. I need to count, right? So let's say int count is equal to 0. Initially, my count is 1 because I'm counting the current node. And returned count plus equals to DFS of count for the graph at u. And then I'll return my count here. Okay, there's probably a lot of bugs here, but we'll give this a go. DFS of u takes in the graph as well somewhere. So 34. Oh, wrong answer. Okay. Oh. Also, if to check if they're actually connected or not. That's kind of important. There we go. Okay. And yeah, this solution took me a while. I haven't actually solved this question yet, so I'm hoping that I've solved it this time around. Had so many wrong attempts. Let's try one of my failed test cases. Oh, this one almost passed. I tried DSU before, but it didn't work. Okay. I'm like 70% confident with this solution. Yes. Awesome. It's so slow though. So the other, I think I'll try again with DSU some other time.